we took interest in this upper tail of the derivative martingale. But what I'm going to do in this talk is to discuss a little bit branching random walk and the derivative martingale in the first part, so to describe the objects that I will be working with. The branching random walk is a particle system on the real line. Starts with one particle at time 0. A little bit branching random walk and the derivative martingale in the first part. Sorry, Nina, I have a bit of back echo with your mic, I think.
I do too.
It's a particle system on the real line. Starts with one particle at time 0. A little bit branching random walk and the derivative martingale. It seems to appear on Nina's sorry, Nina, I have a bit of Nina's mic, if I'm not mistaken. Okay, thank you very much. Sorry. So the branching random walk starts with one particle at time 0, and it evolves as follows. So this particle will create at time 1 a random number of offspring, and the children particles they will displace with respect to the position of their parent according to some point process. Then each of the children will reproduce itself independently of one another according to an independent copy of the same point process with a displacement which is also translated by the position of the parent. So each child particle inherits the position of its parent plus a random fluctuation. And then the process keeps branching forever like this. So at every step, the particles they reproduce independently and create more and more particles over time. So we get a picture like this. And so in the branching random walks that I'm considering, this process works in discrete time. So at every integer time, the clock ticks and every particle reproduces at the same time, so creates new offspring at the same time. So here is a picture of the branching random walk. So I drew here the path of particles in a branching random walk, and I chose the color in such a way that the color of a child is inherited from the color of its parents plus a small fluctuation. So when you look on the right side, particles of the same color, they tend to be marker of families of particle with a close genealogical component. So you see that, for example, on the bottom part of the branching random walk, you have mainly two big families, right? The light blue family and the darker blue family that represent most of the particles at the bottom of the process. Okay, so just to mention this, you can also observe that there is that the branching random walk have a triangular shape, right? So typically the topmost particle and the bottommost particle tend to drift at a linear speed. Okay. So before going any further, I'm going to introduce a few notation. So typically,
Bastien, there was a question about the time being discrete or not.
Yeah. The time of the branching random walk is discrete. So I'm introducing a few notation. So I will denote by U an individual in the branching random walk, and I will write V of U will be the position of the particle U. The absolute value of U will represent the generation to which U belongs. So the root is at position 0 at generation 0. This child is alive at generation 1. This one has generation 2. This one has generation 3, 4, and so on. So, for example, U here is alive at generation 5. And for k smaller than the generation to which you belong, I denote UK, the ancestor at generation k of U. So the branching random walks that I'm considering are always supercritical. So I always assume that on average, a particle creates more than one child. And okay, I will usually also consider branching random walks that never get extinct, so that every particle has always at least one child. But it's not a necessary condition. It's just something to simplify some of the statements. So I will assume the branching random walk I consider to be in the boundary case, which means that the two following integrability conditions are satisfied. So if I take the mean of the sum for all individuals in the first generation of e to the minus the position of the particles, I get something that is equal to 1. And the expectation of the sum of the position e to the minus the position is equal to 0. So those two conditions are not too difficult to be satisfied, because up to a space-time transform, most or a lot of branching random walks can be made to be in the boundary case. So it's kind of similar to how you get a random walk to be centered, right? So not every random walk is centered, but if you remove the drift, you get a centered random walk. So under these conditions of being in the boundary case, so for example, the minimal displacement of the branching random walk has been well studied. And starting from the work of Hammersley, Kigman, and Diggins, we know that the minimum of a branching random walk in the boundary case grow to infinity almost surely, but grows to infinity at 0 speed. So if you see the triangular shape from before, in the boundary case, the bottom part of the triangle just sticks to the x-axis. Okay. So when we are in the boundary case, there are two natural, interesting martingales of interest. So the first one, which I call the additive martingale, which is the sum of the exponential of minus the position of particles at time n. This is a non-negative martingale, and the n, which is the sum of v of u e to the minus v of u, which is a signed martingale. So we assume this condition over here, this integrability condition, which somehow is some kind of a variance, finite variance term for a random walk of interest appearing in the branching random walk. And under this additional condition, we know that the additive martingale tends to 0 almost surely.
So sorry. How v at u is connected with probability? I missed something.
So v of u is the position of the particle u. So it's already a random variable.
Right? Why is martingale? I say why the sum of?
Oh, why is this a martingale? So it's a martingale. It is due to the branching property. So if you look
exponent, at this, exponent, what is v at u? What is v at u anyhow? U uses a number of generations. Or what
is so U is the set of all particles. U goes looks at all particles alive at generation n, right? And so V of U is the position of those particles, and you look at the sum for every particle at a given generation of e to the minus the position.
But why it is martingale? Why the average? Why the average is conserved anyhow?
Sergey, it's by condition. It was assumed.
It's assumed.
No. Expectation is 1. You see it. It's written.
Yeah. So you see that it is a martingale due to the branching property. So if you look at the set of particles at generation n
yes,
plus
but it's
1,
lemma. It is lemma. Why the lemma? The processes don't need a martingale. If geometry, of course, it is not martingale at all. What is condition?
It is a non-negative martingale under the boundary condition assumption.
These conditions. Okay. Right, we'll show once more the conditions. Well,
the conditions are here, right? And this condition tells you that typically from a starting position, you get at the next step a contribution which is exponential of minus your own position. So you get this conserved expectation.
V at u is a weight of the yes. V at u is a weight. Thank you.
So I understand it as a position of the particle, but you can see it as a weight as well particles.
And on the
sorry, we should let the speaker continue, I think, at this point.
Yeah, on the trajectory, the V is the sum of steps.
Yeah.
Sum of steps. So what is V?
V is the sum of steps. So you get a decomposition. If you think of it as weight, you have a decomposition of the weight in the later generations.
Thank you.
So so under those conditions of being in the boundary case, so sum of e to the minus v of u is equal to 1, and sum of v of u e to the minus v of u to be 0, as well as this finite, the finiteness of this third condition. So Biggins and Lyons gave proof that the additive martingale goes to 0 almost surely. And concerning the derivative martingale, so Heidecon showed that under the following additional integrability condition, the derivative martingale converges almost surely to a non-negative random variable, which is strictly positive on the set of survival of the branching random walk. So the derivative martingale, while it is a sign martingale, it converges almost surely to a random variable that is non-degenerate and is positive on the domain of interest for us of the process. And Shen in 2015 showed that the integrability condition given by Heidecon were in fact necessary and sufficient. So those integrability conditions are as such. So you have the expectation of W1 log of the positive part of W1 squared, positive part of the log of W1 squared finite. So this W1, right, is the additive martingale, plus the expectation of W1 tilde log positive part of the log of W1 tilde. So the sum of those two expectations has to be finite. And W1 tilde is the sum of V of u e to the minus V of u, sum over all particles at generation 1, which are positive. Okay, so this integrability condition is somehow a branching with displacement version of the L log L integrability condition for the Galton-Watson process. So for the Galton-Watson process, we know that when we look at the reproduction law of the Galton-Watson process, the martingale associated to the Galton-Watson process converge to a non-degenerate limit if and only if we have an expectation of L log L to be finite. So the analogous in the branching random walk world is this additional integrability condition. So I will refer to condition S as the two joint condition. Expectation of the sum of V of u square e to the minus V of u is finite, and the expectation of W1 log W1 square plus W1 tilde log W1 tilde finite. And under condition S, so I know that the derivative martingale converges toward a non-degenerate limit. And when I add the non-relative condition that there is no lattice on which the branching random walk stays trapped. So when I have this non-lattice condition, I will call the condition S and L. So condition S is equivalent to the non-degeneracy of the limit of the derivative martingale, and S and L allows us to go a little bit further because we break a lattice conditions that can forbid some quantities to converge. So why do we care about the derivative martingale? Yeah, see, it's not the log of W squared, because the log of W squared, right? It's twice the log of W. So it's log W squared. When I write like this, I mean log plus of W1 that I square afterwards. So the derivative martingale appears in the asymptotic behavior of extremal particle of the branching random walk. So this was proved, for example, by Elie Heidecon. So under the assumption S and L, so integrability condition and non-lattice condition, when we set little mn, which is 3/2 log n, then the probability is that the minimum in the branching random walk is larger than 3/2 log n plus z converges toward this quantity. So another way of saying it is that when I look at the minimal displacement, minus 3/2 log n, this converges in distribution to a Gumbel random variable shifted by a quantity which is minus the log of the infinity. Oh, sorry, yeah, shifted by log of the infinity. So the derivative martingale appears in the limit of the minimal position of the branching random walk at a large time. So Madol extended on the result of Aitecon and showed that under the same condition, actually the extremal process of the branching random walk. So if I look at all position of all particles at time n seen from the bottommost particle, then I get convergence to a decorated Poisson point process with intensity given by some constant, which is the same as this one, multiplied by the limit of the derivative martingale times e to the it's e to the z dz, and decorated by independent decorations. So maybe I can try to picture it. So what I claim is that if you look at the branching random walk after a very long time, right, and you look very close to the position, to the typical position of the minimum, you will see a picture that looks like this. So you don't see much, but you see that there is plenty of particles, right? And what I say is that this extremal process, it can be decomposed according to the family to which each particle belongs. So you get the family of the particles that reach the minimum of the branching random walk at a very large time, and it creates a certain point process, which will be my blue point process here. Then there will be a second particle that does not belong to this blue family that will also be able to go very low in the branching random walk. And here it will be my red family, right? And the position of the minimum of the red family is given by, it has an exponential delay with respect to the particle, to the leader of the blue family. And this delay is an exponential random variable with parameter 1. And when I look at my third family, the leader of the third family is delayed with respect to the leader of the red family by an exponential random variable with parameter 1/2. And the next one is delayed by an exponential random variable of parameter 1/3, and then a fourth, a fifth, etc., etc., etc. And you can decompose all the families appearing in your extremal process like this. So the process of the leader will be a Poisson point process with intensity e to the z dz. And for each leader in its family, you get the process of the brothers, cousins, all the extended family of that particle that also contribute to the extremal process, because they are also very small, but they are not as small as their, what I call a leader here. Okay. So yeah, so here is the full extremal process, and full picture of the extremal process. And so to get back to the derivative martingale, it is also used to study the number of particles that are within distance root t from 0 at time t. So particles that move mostly as a centered run, that behave more or less as a centered random walks, that are within distance root t from the minimal position at time t. So Madol again showed that under the same integrability assumption S and L, that for any continuous bounded function f, if you look the sum for all particle at generation f of v of u n to the minus 1/2 multiplied by the weight, so e to the minus the position of the particle, this quantity converges to the derivative martingale z infinity multiplied by this quantity, which is the expectation of f of m1 in priority, where m is a Brennan meander. So a Brennan motion conditioned to stay positive at all time between time 0 and time 1. So this result was later extended by Michel Pain, who proved that when you look at the full trajectory of particles that stays within distance root t from root n from the maximum, you get convergence towards the expectation of a function of the Brillouin meander, but you keep this derivative martingale appearing in the limit. So the derivative martingale tells you to the first order the number of particles that stays within distance root t from the minimal position at time t.
So the f is a function of how many variables anyhow? It's a function of functions.
F is a function of it's a function of the trajectory. So right. So I didn't really write it really clearly, right? But you could imagine this as the trajectory, which would be a step function, right? And if you normalize it in time by n and in space by root n, you get the convergence towards the Brillouin meander. So I didn't write it properly here. Sorry. Okay. So then our objective was to obtain a tight estimate for the left tail of the derivative martingale. And what we showed is that under the assumption S, which is necessary and sufficient for the existence of the derivative martingale, what we could prove was that the expectation of the z-infinity indicator function that z-infinity is smaller than x, this quantity grows as log x as x goes to infinity. And when we assume that S hold as well as the non-lattice as an integrability condition, we also know that this quantity behaves as log x plus a constant plus a little of 1 if and only if some additional integrability condition that I will show later on holds. And so in this case, in the case where this more restrictive integrability condition holds, then we have the priority that the maximum, that the derivative martingale is larger than a large number x, behaves exactly as 1 over x as x tends to infinity. So there was some preliminary results by Thomas Madol under less restrictive conditions here. But the constant was not showed to be equal to 1. So actually, the fact that this constant is 1 over x and not a constant over x is already interesting in itself. Okay, so maybe there are some questions. So before going back to how we proved these results, I would like now to talk a little bit of what happens in the branching Brownian motion settings. So in the branching Brownian motion, most of the things that I'm discussing here are already known. And so I'm going to try to make a comparison between the results in branching Brownian motion settings and our result. So the branching Brownian motion is a process very similar to the branching Brownian walk. It is a particle system on the real line, but now time is continuous as well as space. And particles, they don't move as a discrete time random walk, but as a continuous time Brownian motion. So the branching Brownian motion starts with one particle at position 0 at time 0. This particle starts moving as a Brownian motion. And after a certain exponential time of parameter 1, it divides into a random number that I call L here of children. And each of these children then starts an independent copy of the branching Brownian motion. So they start moving as Brownian motion and reproducing into a random number of descendants after an exponential time. And the process, again, keeps going forever. So if you see a sample path of the branching Brownian motion, it looks something like this. So to the first order, it's quite close to what we saw for the branching Brownian walk. And similarly to the branching Brownian walk, we can, up to a space-time transformation, assume our branching Brownian motion to be in the boundary case. So assume that when I look at the mean of the sum for all particles alive at time t, e to the minus position of the particle, this quantity, I can fix it to be equal to 1. and the expectation of the sum of xt of u e to the minus xt of u to be equal to 0. So in this situation, the derivative martingale is written like this. So it's exactly the same formula as in the branching random walk word, except that it is a martingale in real time instead of a discrete martingale. Okay. So Mallein and Selke showed that for the branching Brownian motion with dyadic branching, so where at every time you split to two offspring, the derivative martingale converges almost surely as time goes to infinity to the infinity, and this result was improved by Yang and Ren that gave necessary and sufficient condition for the non-degeneracy of the limit of the derivative martingale. And this condition is the L log L squared moment, so very similar to what we see in branching random walks, right? So in the branching random motion settings, condition S and L, condition the integrability condition plus the non-lattice condition is only reduced to the condition, the expectation of the number of offspring per branching event times the log of the number of squared. This quantity has to be finite. Okay. So regarding the tail of the derivative martingale of the branching Brownian motion, then lots of results are known. And under those integrability conditions, it is already known, for example, that the tail of the derivative martingale behaves as 1 over x as x goes to infinity. And Maillard went further and showed that under an additional integrability condition, L log L cube, then there exists a constant c, so that this expectation, the expectation of the infinity indicator function that, sorry, the infinity smaller than x, so I made a mistake here, it should be smaller than x. This quantity behaves as log x plus a constant plus a little of 1. So it is interesting that there is here a slight discrepancy with what happens in branching random walk settings, because in branching random walk settings, we were not able to show, and we don't believe that the probability that the derivative martingale is larger than x automatically behaves as 1 over x. It could be that it behaves as 1 over x plus fluctuations that could be quite big, but still, we know that the expectation of the infinity indicator function that the infinity is smaller than x, this grows like log x. So the integral from 0 to x of this quantity does behave like log x, but we don't get the information on this tail exactly. Okay, so what I'm saying is that condition S star that I will come with a bit later is the branching random walk equivalent to the condition expectation of L log L cube to be finite. Okay, so why is this improvement on that tail, so on the probability that the infinity is larger than x to decay like 1 over x interesting? So why is it interesting to have this second order condition? Well, if you know that this quantity holds, then you can get a lot of nice estimates on the speed of convergence of the derivative martingale. And for example, Mallein and Pin showed a much more general result than this, but among others, they showed that if you look at the distance between the derivative martingale at time t and the derivative martingale the infinity, then the convergence happens at speed root t, and you have to shift it a little bit by log t times the infinity to get convergence toward a non-degenerate random variable, which will be the infinity itself multiplied by a spectrally positive one stable Levy, by the value at time 1 of a spectrally positive one stable Levy process by a Cauchy-like distribution. So now let's get back to the branching random walk, right? And how we obtain our results on the tail of the derivative martingale. So what we did is that we looked at the Laplace transform of the derivative martingale the infinity. So what I say is that what I'm claiming here is that the asymptotic behavior of this quantity as x goes to infinity is tightly related to the asymptotic behavior of phi of lambda as lambda goes to 0. So instead of looking at this quantity directly, we looked at the asymptotic behavior of the Laplace transform of the derivative martingale. Okay, so if I want to be a little bit more precise, this quantity here, so the expectation of x, indicator that x is smaller than little x, the fact that this quantity behaves as some constant times log x plus a second constant is equivalent that the Laplace transform of x behaves as lambda goes to 0 as 1 plus some constant times lambda log lambda plus c minus gamma, which is the Euler-Mascheroni constant, times lambda. So having the first three terms of the asymptotic development of the Laplace transform gives us the first two elements of the asymptotic development of this expectation. Okay. So now what we use here is the branching property. So we know that Z infinity is the limit of the derivative martingale, but we also know that the branching random walk, well, it's a step of branching random walk, and then each particle starts an independent branching random walk from their current position. So the derivative martingale has to be equal in distribution to a quantity like this, which is the sum for all particles alive at the first generation of e to the minus the position of the particle multiplied by the limit of the derivative martingale associated to each of the subtrees. So you have a nice identity in distribution satisfied by the derivative martingale of the branching random walk, which almost characterize the law of the infinity. And in particular, it translates for the Laplace transform of the infinity in the following fashion. So we know that phi of lambda now is equal to the expectation of the product for all particles alive at generation 1 of phi of lambda times e to the minus b of u. So we can use the branching property to show that the law of the infinity is a fixed point of a smoothing transform equation. Okay. So now I introduce another function, which is a transformation of the Laplace transform. So I say, okay, so I want to understand the behavior of phi of lambda as lambda goes to 0. And I choose to look at lambda by looking at lambda equals e to the minus x and sending x to infinity. I want to look at 1 minus phi of e to the minus x. And I know that this quantity, I want to show that it behaves as lambda log lambda. So I want to show that this quantity behaves as x e to the minus x. So if I multiply again by e to the minus x, saying that the expectation of the infinity indicates that the infinity is smaller than x behaves as log x plus a constant, will be equivalent to show that the quantity d here, the function d, behaves linearly as x goes to plus infinity. So behaves as x plus a constant plus a little of 1. So instead of looking at the function phi, I will look at the function t. So now I introduce a tameness lemma. So it is known that under the assumption S and L, so then there exists a constant, so that the function d that I look here grows at most linearly with when x goes to infinity. So we know that we have an a priori upper bound on the growth rate of the function t. And what shows that if I know that I have this growth rate that is capped, then more or less the quantity d is characterized. Okay. So now, okay. So I discuss a little bit. So this is the many-to-one lemma. So it's a theorem that allows to compute function of trajectories of the branching random walk by replacing it by a functional applied to the trajectory of a single random walk. And it's interesting for us because it allows us to look at the expectation of my function d at position x plus one step of this random walk. And if I look at this quantity, well, when I remove d of x, I use just the many-to-one lemma. I get that this is equal to this sum, right? The sum of e to the minus v of u, d of x plus v of u minus d of x. And using the special formula that I gave for d, right? E to the x times 1 minus phi of e to the minus x. So I can rewrite this difference as follows. So it is exponential x times the product of phi of the phi of e to the minus x minus v of u minus 1 plus the sum of 1 minus phi of e to the minus x minus v of u. So I have written this difference as the product of quantities that are smaller than 1 minus 1 plus the sum of 1 minus those quantities. And I know that this is always non-negative. Okay. So I know that no matter the value of x that I choose, the expectation of d of x plus s1 is larger than d of x. So now I have two informations on my quantity d, right? I know that it has at most linear growth, and I know then, well, it is a subharmonic function of the random walk Sn associated to the branching random walk by the many-to-one lemma. So, now what I'm claiming is that those two conditions, well, it allows us to describe the function d with quite some precision. Okay, so this is when I talk about the set of subharmonic functions of the killed random walk. So, okay, so I'm looking at a problem like this, right? My function d satisfies a problem like this. So I know that I have a function g that is non-negative and a function h that is bounded, so that my function d satisfies the expectation of d of x plus s1 is equal to d of x plus some positive quantity, right? So I know that the expectation of d of x plus s1 is larger than d of x. So I can write it as, okay, it is equal to d of x plus some additional term. I know as well that for example, the value of d for x negative, and I know that f, or d in my case, has at most linear growth. Well, what I'm looking at is characterizing all solutions of that type of equation. So a couple of simple properties, right? So if I look at a solution of that type of problem, then I know that f of Sn is a submartingale, right? The expectation of f of x plus s1 is larger than f of x, because I assume g to be a non-negative function. And also, I know how to correct this submartingale to get a martingale, right? The f of Sn infimum tau minus the sum of g of sk for k from 1 to n infimum tau minus 1, this will be a martingale. Okay. And okay, this problem P is a linear problem, right? So if I have two solutions and I look at the difference between the two, well then the function g of x disappears in the first equation and the function h of x disappears in the second equation. So the difference f1 minus f2 satisfies the two equations. So the expectation of f of x plus s1 is equal to f of x for positive value of x. F of x is equal to 0 on the negative half line, and f also have sublinear, at most, linear growth. And the set of such functions, so the function that satisfies the three conditions P0, so it is known in a joint work with Gerold Elsmeyer, which showed that when we have an unsorted random walk with finite variance and a function that satisfies all three properties like this, then this function is always the renewal function of the random walk multiplied by some constant. Okay, so there is essentially one function that satisfies all three equations up to multiplication by a constant. Okay, so just to remind you, the renewal function of the random walk is a quantity that you can define like this. So it is non-negative on the positive half line. It is equal to 0 on the negative half line, and u of x grows exactly linearly as x goes to infinity. And okay, so we can obtain similar results for lattice random walks, but in this situation, you won't get this nice constant times u, but you will get yeah, sorry, I didn't talk about the quantity tau that I introduced here. So tau is the first heating time of 0 for the random walk Sn. Sorry, I didn't talk about this. So yeah. So yeah, I introduced it a little bit afterwards. Sorry about that. So now, what I'm saying is that so in our joint work with Darek and Alexander, we showed that if there exists a solution to the Poisson equation that I wrote, then the expectation of the sum from k equals 0 to tau minus 1 of g of sk, where s is a random walk starting from position little x, and tau is the first time where the random walk becomes negative, this quantity has to be finite for all x. And conversely, if this integrability condition holds, and if we have a little bit of regularity on G, that it has to be directly Riemann integrable, then any solution to the Poisson equation can be decomposed as a sum of 3 terms. So the function c times u of x, so the renewal equation solution of the homogeneous equation, plus the expectation starting from x of h of s tau. So you let your random walk works starting from x until the first time where it enters the negative half line. And then you look at h at that position and you add this quantity. So this is more or less an harmonic function of the random walk that will have sublinear growth, and that satisfies the condition that it is equal to h of x on the negative half line, and minus this quantity over here, so which we know to be finite, right, by the first part of the theorem. So we decompose solutions to P as the sum of three parts. Okay. So just to give you some ideas of the method we use for the proof. So the idea is to use the optional stopping theorem on the martingale f of s tau infimum n minus the sum of g of sk from k going from 0 to tau minus 1. And I stop it at time sigma y, which is the first time where the random walk goes above level y. So we know that, in this situation with our assumptions, we can apply the optional stopping theorem. And so we have the equality between those two quantities. And there is also, we have also the limit as y goes to infinity of the expectation of s minimum between tau and sigma y positive part. So basically, the expectation of s sigma y, the expectation of the position at the first time where the random walk hits above level y, on the event that the first hitting time of level y happens before the first time where the random walk goes back to 0. This converges as y goes to infinity to u of x divided by u. So it is this limit is an harmonic function of the killed random walk that grows exactly like x. Okay, so now, so if we assume that there exists a solution to the Poisson equation problem, then we know that we have this equality that holds, right? But we also know that f of x grows at most linearly. So when I let y go to infinity, this quantity on the left-hand side should converge to something like u of x, or at least will be dominated by some constant times u of x. So I know that when y goes to infinity, this quantity is bounded from above. But if it is bounded from above, it has to converge because this quantity is increasing with y. When I increase y, I increase sigma y, so I increase the number of terms in my sum. So this quantity here has to converge, and so has to be finite for all x. Then you look at this particular function, and you show that this function actually it has sublinear growth. So it is a solution of the Poisson equation, and it is a solution with sublinear growth. And because you have this property over here, you can show that it is in fact the only solution with sublinear growth. Somehow, because if you look at this expectation over here, right? Well, at some point where y goes to infinity, you only get the contribution, the expectation starting from x of h of s tau. So yeah, and then you use the linearity and you say, okay, so every other solution is the sum of this particular solution of the equation with the second member plus the general solution of the homogeneous equation. So just to give you an idea, this is what happens in the branching Brownian motion settings. So if we were to look at a similar problem for the Brownian motion, so we want to look at sublinear, subharmonic function of the Brownian motion with at most linear growth. So we know that a function like this would satisfy the second derivative of f is equal to some positive function or some non-negative function with some condition for the value of f of 0. Right? I mean, I know that I won't jump far on the left-hand side if I stop my Brownian motion at the first time it hits 0. So, well, when you solve this very simple differential equation, you get that f of x behaves as a plus some constant times x, so the derivative of f at 0 times x, plus the integral from 0 to x of x minus y g of y dy. Okay. And so now you look at this function and you see that actually saying that f of x has linear growth as when x goes to infinity, well, this is equivalent of saying that x times the integral from 0 to x of g of y dy, this has to converge. This has to grow at most linearly. So when you divide by x, you see that the integral from 0 to x of g of y dy has to converge to a finite limit. So asking f to have at most linear growth is actually equivalent to the fact that the integral from 0 to infinity of g of y dy is finite. And this condition gives you more than f has at most linear growth. It tells you that f has exactly linear growth.
Bastien?
So, yeah, sorry.
A question in the chat about the constant c here.
So the constant c here, so this c times x is about the linear term of the harmonic of the subharmonic function. And so this c, in our particular case, we will show that for the function d on which we apply the theorem, it will be equal to 1. So it is related to the 1 in the 1 over x tail of the maxima of the derivative martingale. The c, the c in our theorem on the precise behavior of the expectation of the infinity indicates that the infinity is smaller than x. This c is related to the second order of the asymptotic behavior of D, so to this constant q here, for example. And we don't have much control on what this constant is. Okay. So yeah, what was that? So I was saying, yeah. So in the Brownian motion settings, you do a little bit of analysis, and you see that f has at most linear growth tells you that f is actually equivalent to some constant times x. And if you want more, if you want that f of x has to be equal to some constant times x plus some other constant plus a little of 1, this is in fact equivalent to the fact that the integral of y g of y dy is finite. And well, we can do the same thing in the random walk world, but without using the differential equation. And we have exactly the same two results over here. So if we have a solution to the Poisson equation, then we know that automatically the function f grows exactly as some constant times x as x goes to infinity. And some, okay, oh, sorry about that, Pascal. So if I add an integrability condition on the function g, so that this limit as x goes to infinity exists and is finite, then actually we get a little more. We get that f of x behaves as c times x plus a constant plus a little of 1, right? So now I can apply these results to obtain the Taylor estimate for the derivative martingale. And the idea is that saying that the function d is a subharmonic function of the random walk with linear growth, with at most linear growth. Therefore, d of x has to be equivalent to some constant time x. And because we have other ways to look at this asymptotic behavior as x goes to infinity, we know that the constant has to be equal to 1. So we know that automatically the Laplace transform of e to the so the expectation of e to the minus lambda the infinities, I should have put -1. This is equal to phi of lambda minus 1, and this has to be equal to, by Tauberian theorem, to lambda, the direct Riemann integrable function, so that you can approach from above and from below by stair functions. So therefore, we know that the Laplace transform of the infinity behaves as 1 plus lambda log lambda as lambda goes to 0. And as a result, we know that the expectation of the infinity indicator function that it is the infinity is smaller than x, this has to grow as log x as x goes to infinity. And so the condition S star under which we get the more complete tail asymptotic for the derivative martingale is written like this. So you can sum it up by saying there is an L log L cube condition. So it is the analogous of the L log L cube condition for the derivative martingale of the branching Brownian motion. So you get something like the sum of e to the minus v of u cube is finite. We have a condition, the expectation of two quantities that are related to W1. Log W1 cube has to be finite. And we have the W1 tilde, log positive part of W1 tilde squared, that has to be finite as well.
Sorry, what is DRI function previous slide?
So
DRI function, what is it?
DRI function is a direct Riemann integrable function.
Oh, okay.
Right. Sorry, yeah. So now, then, what was needed to prove is that this integrability condition S star is actually equivalent to the fact that the supremum for x in R of the expectation starting from x of this sum is finite. And because we have a little bit of structure on the function g, we also obtain that if this supremum is finite, then the limit exists, always exists somehow, because g is not exactly increasing with x, but it's almost increasing somehow. So we get just enough structure so that we can show this limit to exist. And this is enough to say that S star is equivalent to the fact that there exists a constant, so that d of x behaves as x plus this constancy plus a little law of 1. And this, by the Tauberian theorem, tells us exactly the asymptotic behavior of the derivative martingale, of the expectation of the derivative martingale. Okay. So condition S star can be simplified a little bit if you make a simplifying assumption on the way the branching random walk behaves. So if instead of having this point process of children, you say, okay, so my branching random walk, it makes a random number n of children, and then each of its children, it moves independently according to an independent copy of the same random variable x. Then, well, condition S, really looks like the condition for the branching point motion, right? We have this expectation of n log n squared to be finite, and the expectation of x squared e to the minus x to be finite as well. So this is the finite variance assumption, and it is automatic, of course, when you look with brane motion. And the condition S star then right, so the expectation of n log n to the cube has to be finite, and the expectation of x to the cube e to the minus x has to be finite as well. So I should have put the x positive part, but okay. So just a last remark is that with the nice tail that we get on the expectation of the infinity integrator function that the infinity is smaller than x, so at the integrated left tail, the integrated tail function of the derivative martingale, we also obtain a small central limit theorem for the convergence of the infinity. I mean, I say small with respect to the result of Pan-Maillard, which had the central limit theorem at several positions at the same time. And we get that the infinity minus the n behaves as some spectrally positive one stable random variable times the infinity over root n plus root log n wn times root n, something like that. No, there is no convergence of process here. We were not able to get the convergence the infinity minus the a times n plus log n wn as a function of a. And yeah, some additional results should be needed to obtain this. Okay, and so I think I will stop here. Thank you very much for your attention. So S, sorry, it's a value at time 1 of this Levy process. Yeah, I should have mentioned it. Sorry about that.
Thank you very much for this lovely talk, Bastien. I suggest that we unmute ourselves to give Bastien an applause, and I will stop the recording. So, are there questions or comments which were not already given during the talk? There is one question in the chat. Why S is a Levy process?
Yeah, so sorry, I made a mistake in this slide. So S is not a Levy process; it's a value at time 1 of this strictly positive one stable Levy process.
This was related to the previous question. So
yeah.
So S is a Levy process, but here you have the value.
Yeah. It's just a stable random variable.
But the conjecture is that you would really have a convergence of processes at this point.
Yeah. So, and the convergence of processes is a bit complicated, right? Because you would get like the infinity minus z at time a times n, and this would converge towards the spectrally positive Levy process, but with a time change. So that, right, when a becomes large here, the value of the Levy process has to go small because you converge to the infinity, right? So when a goes large here, you get the Levy process at S at position 1 over root a or 1 over a, something like this. Okay, so.
Sorry, what is SNI condition? SNI?
SNL,
Yes.
sorry. So it's the usual integrability condition for the branching random walk. So in addition to the derivative, and NL says non-lattice.
Actually, there's a
non-lattice or convergence. What is it? SNI it is non-lattice, or it is moment condition.
The moment condition is the expectation of W1 log of W1 squared to be finite. So condition S is, no, sorry, I went too far, I think. No, I went not far enough. Here, right? So condition S is those two integrability conditions, and then we have to add this non-lattice condition.
So
And the non-lattice condition is helpful here because if you assume your random walk to be lattice, then you can only so when you think about the subharmonic function, for example, well, you can only relate the value at 0 of this solution to the value at any other point on the same lattice. Right. So if you assume that your random walk is on Z, has integer steps, then you can only relate the value at 0 of this function to the value at any other integer of the function. So for each
W tilde
number between 0 and 1, you get a C, which is associated to this number that tells you. So if I am at Z plus 0.3, then I grow like C of 0.3 times X. And so it is this periodic function that is bringing some complications in our settings, but we don't always need the non-lattice condition. So I said most of the result in the case where it's non-lattice because you have a constant and not a periodic function, but I mean, a lot of results extend to the lattice case.
Sorry, what are W1 and W1 tilde?
So W1 is this, right? It's the value at time 1 of the derivative martingale. And W1 tilde is here, the sum of positive part of V of U e to the minus V of U.
Thank you. Thank you. Thank you.
Okay, so there don't seem to be further questions. So I suggest that we stop here and we have a 5 minutes break before the second talk.
So, thank you very much.
Thanks again, Bastian, for this lovely talk. Maybe Hui, you can share now already.
Okay. Fine.
What time is it for you?
Perfect.
Okay, thank you.
And I will restart the recording at some point. And Julien, do you want to chair now?
Yeah, sure. What time is it for you, Hui?
Fine. I mean, do we still have some time to have rest? Or
yeah, we have a couple of more minutes, but I was asking what time it is for you.
11 p.m.
11 p.m. Wow.
Yeah, we're lucky actually, because I mean, around the world it can be problematic with the time shift. So I remember I was wondering when I asked you if you would accept, but then you said yes, and then I didn't think about the time shift
around 12, yeah, so it's fine.
Okay, I will start recording.
My computer reminds me that it's recording.
So we should start, yeah?
Okay.
Sorry?
Okay, fine.
Okay. So for our second talk, we have the pleasure to welcome Hui He from Beijing Normal, who is going to talk about deviation probabilities for maximum of a branching random walk. Floor is yours.
Okay, thank you for the introduction, and also thank you for the invitation. This is my great pleasure to give a talk here. And in the previous talk, in fact, Bastien already said something about branching random walk. And in my title, there are three key words. So the first is the derivation probability, then the maximum, then the branching random walk. And in fact, the two of them was already mentioned in Bastien's talk, that is the branching random walk and also the maximum. In fact, in Bastien's talk, he talked about the minimum, but if you consider the opposite, you get the maximum, right? So there's only 1/3 task left for me, okay? And my talk will contain the 2 parts. And comparing to Bastien's, there are 5 parts, right? So, okay, so please be relaxed. Okay, I only need a short time for that. And a different with him that I would like to talk first about the branch bending motion. Then I will talk about the branching and walk. I will recall some basic facts about these 2 models to make my own talk self-content. And some of them was already mentioned in Bastien's talk. So first, I would like to recall the definition of branch bending motion, okay? And my definition is a little bit simpler than Bastien's. So branch bending motion is a particle system. And in this particle system, each particle moves as a bending motion. And also each particle has a random lifetime distributed exponential 1. So when the lifetime ends, it will have 2 offsprings left. And then each offspring will perform the same behaviors. That is, each offspring moves as a bending motion, and each offspring also has a random lifetime distributed as exponential 1, okay? So look at this ugly picture. I know that there are many nice pictures in Bastien's, okay? So I draw this picture by mouse. I'm sorry for that. And so at the very beginning, there's only 1 particle starting from the orange, and it moves as a bending motion, okay? So it seems to be not as a bending motion, but you can imagine it's a bending motion. So when the exponential time or exponential clock is open, so the particle dies out, and then there will be 2 offsprings left, and these 2 offsprings starting from the place they were born, that they moves as a bending motion, and each of them still has a random lifetime of exponential 1. So for example, this particle moves as a bending motion and is quite lucky, it has a longer lifetime. And this particle, the lifetime of this particle is quite short. Okay, then it dies out again here, and then the 2 offsprings are left, and each of them still moves as a bending motion. So our concern is about the maximum position of all particles alive at time t. So that is mt here. And let us look at this picture again. So at the very beginning, there's only 1 particle, okay? So it starts from here. So at the very beginning, mt is just this curve. And then there are 2 particles, that means 2 curves. So mt is this curve, that's our boundary, because we want to consider the maximums. And then this one, okay? So this, you can imagine this is a graph, and then the mt just up boundary of the graph. Okay, so this is just our mt here. So as I said, in the picture is ugly, so I steal the one from Mass Robots. It's not mine. Okay, and then the particle, there's 1 particle starting from here. It moves as a bending motion. Please notice that in this picture, when the particle dies out, there are more than 2 children, I think, here. And I also would like to mention that the exact value of the parameter 1 here is not important, and also the exact value of the number of individuals is not crucial to our argument. And it could be 2 or 3 or 4, and it also could be random. What we really need is that the mean of the number is larger than 1, and also we need some technical conditions as talked in Bastien's, as mentioned in Bastien's talk, okay? So in this picture, you can see that when the particle dies out, it may have 2 or 4, 4 or 5 children, right? And then each of them moves as a bending motion, okay? So the mt in this picture is just this one. You may think it's just the boundary of this graph, okay? The up boundary of this graph is just our mt. And then there's a deep connection with this mt to a PDE, that is Mallein in 1976. And he considered the following space-time function, that's the probability that the maximum is less than x. And he shows that this spacetime function defined in this way satisfies the following nonlinear PDE. Okay, this is a nonlinear PDE, and you have a nonlinear term here, U square. And also would like to mention that in my setting, I assume that when a particle dies out, there are only two children left, okay, two offsprings left. So if we replace the number of strings by something else, for example, there are three offsprings, and you have two square by u square by u to the 3, okay? If we replace the number, if the number of offsprings is random, then you just replace the u square by the corresponding duality functions. So with these connections, Bramson in 1983 get the weak convergence of the centered maximum. As we already see that since when each particle dies out, then two children are left. So and there are more and more particles.
The initial position of the point.
Sorry?
From what point the Brownian motion start? From the 0?
Yeah, yes, true. At the very beginning, the ancestor start from 0. Okay. So MT will go to infinity as T go to infinity. So Bramson found there's a normalized function that is, if you centered with little mt, and this little mt is just square root 2t minus 3 over 2 square root 2 log t here. And this will converge weakly to some other functions that is on the right-hand side. Omega x is a distribution function. And I think it's also mentioned in Bastian's talk that Mallein and Silk showed that this distribution function could be represented by the limit of derivative martingale. And in fact, in his talk, he mainly considered the tail behaviors of this of the limit of the derivative martingale. However, in my talk, I will mainly consider this probability. Okay, this probability. So I shall turn to my interest. So recall that Bramson shows that the maximum position of the branch bending motion, that is capital MT, centered by this little mt, converges weakly. So our interest is the so-called deviation probabilities. And for this interest, for example, if AT, it is a deterministic function which go to infinity, as t go to infinity, then there are two kinds of deviation probabilities. The first is about up deviation probabilities. That is, we consider this probability, that is, we know that MT centered by little MT converge weakly. So you plus AT here, this probability will go to 0. So we want to know the decay rate. And then we consider the opposite direction, that is the capital MT less than little MT minus AT. And again, we know that this probability go to 0. We also want to know the decay rate of going to 0. So first, I would like to give some recent result on the up deviation case. So there are two subparts. One is up deviation, the other one is lower deviation. And we recall Bramson's result again, I'm sorry. And it was shown by Bramson that the MT goes to infinity, like square root 2 minus log t term, okay? Then Chauvin and Olong in 1988, they considered the following probability. That is, for alpha larger than 1, they consider the probability that MT is larger than square root 2 alpha t. Since from Bramson's result, you know that the first order of MT is just square root 2t, right? It's linear and with square root 2. And if you consider alpha larger than 1, so this probability go to 0. And Chauvin shows that the decay rate is just this function that is constant over square root 2 times some exponential part. And later, Auguin, Bouvier, and Christina further give an explicit form of this constant via the solution of FKBP equation. And also need to mention that this constant, in fact, depends on alpha. And in Chauvin and Holland's work, they only show that there is a constant. And in Auguin, Bouvier, and Christian's work, they give an explicit form, and they know that this constant depends on alpha. And later, Brasky, Brunit, Cortina, and Mallein, they also show that further study this constant, that they give another representation of this constant as a function of alpha while some probabilities, okay? Since René and Bastien are in the audience, you may ask them for the details. So next, I would like to give a rough idea about this updivision probability, that is y, as t go to infinity, this updivision probability decays in this rate. Here I replace the constant by C alpha. This means the constant depends on alpha, okay, for alpha larger than 1. And we need 2 facts for this result. The first fact is that the number of particles at time t, we denote by nt. As I already mentioned, each particle has a random lifetime distributed as exponential 1, right? So this means the total number of particles in the system grows exponentially, and in average, this the number of particles at time t is just e to the t, okay? So this is a simple fact. In fact, it's not difficult to prove it, or quite easy to see it. And another fact is each particle moves as a Brownian motion. This, of course, know from the definition of the Brownian motions. And each particle, when each particle dies out, the offsprings just start their own motions from their ancestors. So each of them moves as a Brownian motion. However, they are not independent, right? Because they share the same path from their ancestors. So now we want to know the updivision probabilities, that is mt larger than square root of alpha t. So recall that mt is just the maximal position at time t. So what does it mean? It just equivalent that there exists one particle whose position is higher than square root of alpha t, right? Since mt is the maximum, so the maximum is larger than something, larger than some value. It just means that there is one particle at time t and whose position is higher than this value. Then according to the union bound, okay, we can use the union bound. I should mention that the particles are not independent because they share the passes from their ancestors. However, according to the union bound, if we want to know the upper bound of this probability, just that it could be bounded by the summation of all probabilities that each particle each particle position is higher than square root of alpha t. So this could be bounded by the total number of particles times the probability that each particle's position is higher than this value. And we use these 2 facts. The first fact is that the total, in average, the total number of particles is e to the t. And the second fact is that each particle moves at a Brownian motion. So the probability that each particle's position is higher than square root of alpha t is just the Brownian motion at time t, whose value is larger than square root of alpha t. Okay, and we also know that bt is normally distributed with mean 0 and 1 t. So you get the following quantity, that is to the e to the t times this integration function, and then as t go to infinity, okay, so this quantity is just equivalent to this one. So to see this, you keep the et as same before, and to understand this asymptotics, you just according to the Gaussian tails, you just put the square root 2 alpha t inside of x. So we get e to the power minus 2 alpha square and t square, right? It's a square root 2 alpha t. So you put it inside into the x. So you get 2 alpha square t square over 2t. Then you cancel 2 and 2, you cancel t and t square. So you get alpha square t left. Remember that there's another et here. So then you get this form. It's 1 over square root t times this exponential function. Then you can see the function in the blue, it's just this one, okay? It matches, okay? So please notice that the argument here is strict, okay? It's a strict argument. However, this is just give you upper bound. That is means that you just need a simple first moment argument, that is the union bound argument. You can get the exact decay rate of this probability, but it's just you just get upper bound. And of course, it's hard for you to get the constant according to the explicit constant according to this argument. And then for the lower bound, one need a refined Bremont-Zone's argument on the FKBP equation, okay? And in this case, much more details are needed. I would not mention it. And also, if you want to know the piece form of this constant, and the work will be much more involved. So I would like to stop here for the story of up deviation for the BBM, and then next I shall turn to the story for the Noyer deviation for the Brownian motion. So for the Noyer deviation case, Dahida and Shi in 2017, they consider the following probability, that is for alpha less than 1, they consider the maximum position at time t is less than square root 2 alpha t. So for alpha less than 1, we already know that the first order of capital MT is just square root 2t, right? So this property shall go to 0 as t go to infinity. Then Dahida and Shi take a logarithm of this property. They show that after taking the logarithm of this property, and it decays according to the function on the right-hand side. And on the right-hand side, we have a function. It's a linear function with respect to t, and also we have a term phi alpha here, and this is also a function of alpha. Okay. However, there's a phase transition phenomenon for this phi alpha. That is, if alpha is larger, I mean alpha is between 1 minus square root 2 and 1, then phi alpha is a linear function, and if alpha is less than 1 minus square root 2, is 1 plus alpha square. Okay. So then there are two natural questions coming into my mind. The first question is why there's a phase transition phenomenon according to this alpha. That is why why the phase transition for alpha is when alpha is at 1 minus square root 2. And also second question is that can we remove the logarithm? That is, can we obtain a more precise asymptotics for the decay of this probability? So first we need to understand why this phase transition phenomenon happens at 1 minus square root 2, okay? So this is a picture for the phi alpha. So before minus gamma, here minus gamma is 1 minus square root 2. It's a linear function. And on the left-hand side, it's 1 plus alpha square, okay? So here you can see this, there's a phase transition phenomenon of the form of phi alpha. So in fact, the phase transition happened at 1 minus square root 2 relies on the following fact, that is whether the first branching happens before time t or not. So let us go to this picture again. That is, sorry, I have to show this ugly picture again. And first, as I said before, there's only one particle starting from the orange, okay? At time 0, there's only one particle starting from orange, and it moves as a Brownian motion, and it also has a random lifetime distributed as exponential 1. So this is just the first branching event, because this is the first time that there's a particle that the ancestor dies out. So first branching happens before time t or not, it means that the lifetime of the ancestor is larger than t or not. Okay, if the lifetime of the ancestor is less than t, this means the first branching happens before time t. If the lifetime of the ancestor is larger than t, it means that the first branching happens after t. Okay, so this is just a first branching event. I shall show why this is true, in fact. So we first let us to see why you get Dahida and Shi get this result, that if alpha is less than 1 minus square root 2, the decay rate of this probability is like this function here. Okay, since in Dahida and Shi's result, they take a logarithm of this probability, then you get 1 plus alpha square times t. So this means that this probability decays as this exponential function, and here you have O1 term here. So if alpha is less than 1 minus square root 2, we want to understand the maximum position at time t is less than square root 2 alpha t, okay? And as I said, if alpha is very small, it means that there's the lifetime of the ancestor is larger than t, okay? So there's a natural lower bound for this probability, that is, we make a restriction that there's no branching occurs before time t. That means the first branching event happened before t, or it also means the lifetime of the ancestor is larger than t, okay? And so as we already know that the lifetime is random distributed as exponential 1, so the probability that there's no branching occurs before time t is just e to the minus t here, right? And we also know that since there's no branching occurs before time t, it means that at time t there's only one particle that is just an ancestor. So since at time t there's only one particle that is the ancestor, so the maximum position at time t is just the position of the ancestor, okay? And because there's only one particle, that just itself, right? So mt is just the position of the ancestor. And we also know that the ancestor moves as a branching motion. So if we make a restriction that there's no branching occurs before time t, so mt is just bt, okay? So this probability is equivalent to e to the minus t times the probability that the branching motion is less than this value. So again, we know that branching motion is bt is normally distributed with mean 0 and 1 t. You get this formula that is 2 minus t times this function. Okay, you get a minus infinity integration from minus infinity to square root 2 alpha t here. And again, according to the tail behavior of the Gaussian functions, we have seen that at t go to infinity is somewhat equivalent to another function, that is, you just put the square root 2 alpha t inside of x. So you get this formula, that is 2 e to the minus t times this function. You just put the square root 2 alpha t inside of x. So you get 2 alpha square t square over 2t here. Then again, you cancel 2 and 2, you cancel t and t square, you get alpha square t left. Remember that there's another e to the minus t before, so you get this function that e 1 over 2 square 1 over square root t and e to the minus 1 alpha square t. So you can see that this is the exact same to what obtained by Dahida and Shi. Okay, so this means our intuition is right. Okay, so it's right that if alpha is very small, it means that if we want to get a right decay of this probability, you just assume that there's no branching occurs before time t. Okay, this is just the intuition. So if alpha is not
this lower bound holds for any positive alpha,
right?
This lower bound is okay for any positive alpha.
Yeah, but this is not right, not the right bound if alpha is larger.
No, the role of this bound, alpha is small, 1 minus root of 2.
Yeah, true, it's true. Yeah, if alpha is less than 1 minus square root 2, it's already true. Yeah, it's the right bound.
So sorry, but alpha is smaller than 1 minus root of 2. It means alpha is negative, correct?
Yeah, true. It's alpha is negative. Yeah, alpha could be negative. Okay. So if alpha is larger than 1 minus square root 2, it somewhat means that the lifetime of the ancestor should be less than t. That means the first branching event happens before time t. So more precisely, we have some other result. That is, if alpha is very small, that means alpha could be negative. Okay, alpha is very small, then the ancestor starting from the origin moves as a branching motion, and its lifetime is just very near to the t, because we need to get an optimal rate for the probability that mt is less than square root of alpha t. So we just let the first branching happens very near to the t, and the position of the particle where the particle dies out is just very near to square root 2 alpha t. Okay, so this means tau is very near to t. Okay, with some up to some constant. So if alpha, this is for the alpha less than 1 minus square root 2, and if alpha is larger than, strictly larger than 1 minus square root 2, you have something like that. Then at the very beginning, you have one particle which starts to move as a branching motion. Then it will go down to some very low position, be tau, and the tau is just his lifetime. And then it dies out and has 2 offsprings here. Okay, after that, there are 2 offsprings, and these 2 offsprings will involve as 2 independent branching motions. And these 2 independent branching motions will involve as a Euro branching motion. Okay, so in this picture, you can see there's one branching motion that is the green curve, and also the yellow curve is another one branching motion. And these 2 branching motions involves as Euro. This means they are, they are regular branching motions. Okay, there's no restriction to them, and these 2 are independent. And this is the position that these 2 independent branching motions start from. So what we want is that the maximum of the whole system at time t is less than square root 2 alpha t. This means that it's hard for these 2 branching motion to reach this level. Okay, so we also know that in average, the height of this, the maximum of these 2 branching motions is just t is just little mt minus tau, because they start their motion at time tau. So at time t, the height of these two branch band motions should be less than square root 2 alpha t. So the position here, b tau, should be around square root 2 alpha t minus little m t minus tau here, and the tau should be less than t, that it should be around.
It's the difference between O and theta capital, O1.
Sorry?
This one, yes. What is the difference?
Okay. This is a constant. In fact, it's later we'll show that it's a random variable. It's a finite random variable. Okay.
What O capital? O capital is the same. What's the difference? What is the difference between these two signs? Theta capital.
Oh, sorry, you mean the theta 1 and O1, right? Here it's also finite terms. It's also finite terms. Both you can imagine it's finite terms. Okay. As t go to infinity, both are finite terms. Okay.
Okay.
So the fluctuation is square root 2t, square root t. Okay. So this is for the alpha is larger, and for alpha it's just 1 minus square root 2. It's a little bit different with the alpha, with the case that alpha less than 1 minus square root 2. So we still have one particle starting from the orange. It moves at branching motion, and we let it go down to here, and the first branching event is around this. It's around here. If we may go back to the previous picture, that when alpha is less than 1 minus square root 2, it's the tau should be like this one. That's t minus O1 term, that is quite near to the time t. However, if alpha is just 1 minus square root 2, and tau is still be near t, but however the fluctuation is square root t here. Okay, and we still need to let the position of the particle where it dies out is around this term, that is square root 2 alpha t minus this term. Okay, so with this careful analysis about the tau and b tau, we can obtain the following result. That is, with Xing and Mallein, we obtain that as t go to infinity, this probability decays according to the rate, according to the function on the right hand side. That is, when alpha is between minus gamma and 1, that is here gamma is square root 2 minus 1. Okay, that is 1 minus gamma, between 1 minus square root 2 and 1 here. And the exponential term is already obtained by Dahid and Shi, and the way obtained is that t to the 3 gamma over 2 and the constant C1. And if alpha is just minus gamma, then the power term is that t to the power t to the 3 gamma over 4. And if alpha is very small, here notice alpha could be negative. Okay, if alpha is very small, and that you get 1 over t here. Okay, and here C1, C2, and C3 are 3 explicit constant depending on alpha, and also the form, the explicit form also depends on the KPP equation and the omega x, that is the distribution function of limiting distribution function of the centered maximum. In fact, this result in Dahid and Shi, in another paper by Dahid and Shi, they give a heuristic proof of these results. Okay, so I also would like to mention about the case of the first branching event. Here, to save the time, I only mentioned about the first branching time. So if we condition that the maximum position at time t is less than square root 2 alpha t here, then if alpha is larger, then the first branching time is around this value, and the fluctuation is just square root t. Okay, so then as t go to infinity, this quantity will go to in distribution to the limit is normal distribution, and if alpha is just 1 minus square root 2 and t minus tau over square root 2t go in distribution to some random variable c. In fact, we know the explicit distribution function of c, and c is a positive or random variable. And also when alpha is very small, the first branching time satisfies this limit. This means tau is very near to the t. Okay, this t minus t of tau converges weakly to the some another random variable, and also we know the form of this random variable is also positive. That is, we know the distribution function of this random variable. Okay, so we can also understand the b tau and the extremal process, but I shall omit the details here. So this is a whole story that I want to mention in this talk about the case of branching and bending motion. Next, I shall turn to the case of branching random walk. Okay. So for the case of branching random walk, I would like to give some definition about the branching random walk. My setting is a little bit different with Bastien's because in Bastien's talk, he considered the offsprings in forms as a point process. But here, I would assume that the branching and motions are independent with each other. So I would like to regard the branch random walk as a discrete counterpart of branch bending motion, and I still denote by Mn be the maximal position of all individuals alive at time n. So let us see the following picture for the definition of this branch random walk. So at the very beginning, there's only one particle starting from the orange, okay? And then it may have a random number of children. And in this picture, I only show that it may have two children, and each of them do a one-step random walk, okay? Given according to a given law of step size. So there are two particles in the first generation, and the position of these particles is just M1, okay? Since it's higher than this blue one, the red one is higher than the blue one. And then we get the next generation, and so this particle has two children, and this particle also has two children, and each of them still do a one-step random walk according to a given law. That is, the law is called the step size. So there are 4 individuals in the second generation, and we still denote by M2 as the maximum position in the second generation. The position of this particle is just M2, okay? And then you get the third generation. So this particle may have 2 children, and this particle may also have 2 children, and this one only has 1 child, and this one also has only 1 child. And again, each of them do a one-step random walk from the starting from their ancestors. Okay, so there are 1, 2, 3, 4, 5, 6 individuals, and in the third generation, and then the position of this one is just M3. So then you get the fourth generation here. So this is just M4. So M1, M2, M3, and M4 are just the maximum position in each generation. So Mn is the maximum position of all particles at time n. And then I need to recall some basic results. And since my my setting is a little bit different with Bastien's, so the result printed here seems to be different with him with what was printed in his talk. But in fact, the basic idea is the same. That the Biggins, Hammerstedt, and Kieman shows that Mn go to infinity almost surely with the rate x star. Okay, and here x star is a constant depending on the offspring law and also the step size. And later, Adorberry Reed and Hu and Shi, they get a second order, that is, you get a logarithm corrections for this Mn here. And here y star is also another constant depending on the step size and offspring law. And then I dig on some mild conditions. In fact, this mild condition is just the conditions SNL mentioned in Bastien's talk. Please remember that the form is different, but the the basic idea behind it is the same. That we also need the step size is non-lattice, and also we need that the offspring node satisfy the so-called n log n square conditions, and also the step size satisfies the exponential movement conditions. Okay, then you get that Mn centered by this function converges weakly. This was shown by Adigon in 2013. And then you can see that
what is OP?
Sorry?
OP of logarithm, OP, yes.
It means that this term over log n converges to 0 in probability.
In probability, okay.
Okay, sorry, yeah.
Okay, thank you.
Mm-hmm. So this result could be seen regarded as a parallel result to Bermanson's one. Okay. However, there are 2 difficulties. The first difficulty is that there's no PD method, since for the branch bending motion, you can connect MT to the FKP equation. And the second difficulty is that there's no Gaussian displacement. Okay, because in the case of branch, in a setting of branch bending motion, each particle moves as a bending motion. However, here the the particle just do a Euro random walk, and the step size could be quite general, so there's no Gaussian displacement. And in this talk, I can assume that identical conditions are already in force. And I also would like to mention that this condition just as an error condition in Bastien's talk, if you can remember the condition mentioned in his talk, okay? And this just identical result, that is the Mn go to infinity according to like this curve, and this curve just x star times n minus y star times log n here. And then there are also two kinds of deviation probability that I would like to concern, that upper deviation probability and the lower deviation probability. And then some notations are needed, okay? So first, denoted by C, the number of springs, and X be the step size. So I assume some basic assumptions are also needed. First is that the probability that C 0 is 0. This means that when a particle dies out, it has at least one particle left, okay? And then we assume that the number of springs is 1 is less than 1, okay? If it's 1, it's just a simple random, it's just a Euro random walk, it's not a branching random walk, okay? So we try to avoid the trivial case. So we have these assumptions. And then we assume that the EX, that is the mean of the step size, is just 0. And also we assume that the step size has exponential moment. However, should be noticed that here lambda is larger than 0. So it means that the right tail of the step size decay exponentially, okay? And the left tail will be play a crucial role in our results. And then under this setting, and you can define the X star here, that is I mentioned in the previous slide, that is the first order of Mn. The rate of the first order of Mn is just this constant X star. It can be defined as this one. And here, Rx is a Euro Laurent transformation for this capital X, okay? And then so we consider all the value of Ix is less than the mean of the offspring, which denoted by m, little m, be the mean of offsprings. So Ix is just a Euro rate function for the general random walk with step size capital X, okay? So with this notation, we get the following result. That is countered by Hof's law in 2018. They show that if X is larger than X star, they consider the following probability. That is, Ma is larger than X times n. Since X is larger than X star, we know that this probability go to 0 as n go to infinity. Then take logarithm, then you also take 1 over n here. You get a limit is just Ix minus logarithm of m. Okay.
Sorry,
so m,
log m.
Sorry?
Log m have to be the condition, no? Here.
Which one?
Log m. Huh?
Yeah.
M
No,
or
m.
log m?
Yeah.
Ah, okay.
It's logarithm of the mean of the offsprings. Sorry. Okay. So the basic idea to this result is somewhat similar to the case in the branch bending motion. That is, you can just compare the maximum of a branch random walk to the maximum of independent random walks. Okay, as we showed in the case of branch bending motion. Okay, if we want to see the R bound, you just consider you can use the union bound. Then you just regard each particle moves independently. So, and then you can see that if we want to let Mn be larger than X times n, how to do that? As we said, it can be compared with the maximum of independent random walks. So in average, okay, since M is the mean of the offspring node, so at time n, in average, there are m to the n particles in the systems, and then each particles moves as independent random walks, okay? Here Sn is just a Euro random walk with step size of capital X. So this just means that this probability is equivalent to m to the n times a Euro random walk whose position is higher than xn. And we know that this probability is just this one, okay? Since Ix is a rate function of the Euro random walk. So you get Mn times e to the minus Ix times n here. Then you take logarithm for this term, you get that is Ix minus log m, okay, right? So this gives
you the definition of X star, you have forgotten the logarithm, because you see, M in the log M. Here.
Sorry. Okay.
Mhm.
Thank you very much. Okay. So this is just a rough idea for this result, and this is for the case of up deviation. And then we shall turn to the case of the lower deviation. We still denote by Kc of the number of springs and x be the step size. However, the case of lower deviation is much more complicated. There are several subcases should be considered. The first subcase is the so-called Schroeder case. It means that we consider that the number of springs could be 1. That is, the probability that Kc is 1 is positive. Okay, so this is just the so-called Schroeder case. This means when a particle die out, it may just has only one child left, and we further assume that the step size x has exponential moment that not only the right tail but also the left tail decay exponentially for some lambda positive. Okay, so under this assumption, Ganti and Hofstadter law also shows that for x less than x star, this probability, that is mn less than xn, this probability go to 0 at n go to infinity. So then you take logarithm of this probability, you take 1 over n here. This quantity as n go to infinity will converge to the limit on the right hand side. However, this it is a little bit complicated. Let me explain a little bit. This first gamma is a so-called Schroeder constant. That is take logarithm of this probability. Okay, this is just a probability that the number of springs could be 1. Okay, take logarithm is just a so-called Schroeder constant. And IA is just defined in the previous slide. That is the rate function of Euro random walk. And the idea to this proof is that if we want to consider the Mn less than Xn, since we are in the Schroeder case, that is when each particle dies out, it may has only one child. So for the lower bound, we just force that at the very beginning, when each particle dies out, it can only has one child. So we want to find some intermediate time Tn that before time Tn and each particle only has one child. So we have this probability to the Tn. And since each particle only has one child, okay, so at time Tn, there's only one individual in the systems. And so from time 0 to time Tn, it's not a branch random walk. In fact, it's just a Euro random walk. So you let the position of this individual to be lower than some special positions. Okay, here we also need to choose a suitable A. So then this probability will behave like this one. That is, you only has one child before some intermediate time Tn, and at time Tn, this individual, the position of this individual is less than A less than A times Tn here. So after that works, since there's only one individual at time Tn, so after that, this only one individual can be seen as a new branch random walk. It just start from A times Tn, and then this branch random walk involves as Euro. Okay, but since the position is very low, so it's hard for this Euro random walk, branch random walk to achieve Xn. Okay, so this means then the maximum, you get the maximum of the whole system is less than Xn here. So that's why, since you need to take logarithm, that's why you have gamma in this term, and also you have the Euro random walk, and so that's why the IA appears in the limit. Okay, this is why gamma and IA appears in the limit. So this is the best idea for the lower bound, and for the upper bound, just to prove that this idea is optimal. Okay. So this is for the lower deviation for the Schroeder case. Next, we can turn to the Bochner case. For the Bochner case, there will be 3 sub-cases that we need to understand. But again, we denote by Kc be the number of springs and x be the step size. And here we assume that the Kc is larger than, the probability that Kc is larger than 2 is just 1. Okay, so this means that when a particle dies out, it at least has 2 children. Okay, at least has 2 children. This means that the number of individuals grows exponentially. Okay, there are more and more individuals in the system. It grows exponentially, almost surely. And then we need to introduce another notation, that's a little b here. So what does mean by little b is just that here you see you take the infimum for all the k such that the number of individuals could be could be k. The probability that number of individuals could be, a number of springs could be k is positive. Okay, so this means the minimum number of all possible possible offsprings. So this just need to be. Then the first result we get that if the left tail of x behaves like this function. Okay, please remember that we already assume that the right tail of x decays exponentially. Okay, here we assume that the left tail of the x decays according to this function. So it's e to the minus lambda the alpha. Here lambda and alpha are positive constant. And if we say that if alpha is less than 1 is sub-exponential decay and alpha is larger than 1 is super exponential decay. So as we see, if the left tail of the step size decay at this rate, you get the lower division probability also decay exponentially. However, after take logarithm, the rate function is 1 over n alpha here. So this alpha is same to this alpha. And on the right-hand side, you get the limit. However, there also a phase transition phenomenon according to alpha. So if alpha is larger than 1, this means that the left tail of the step size decays super exponentially. You get this form. And alpha is less than 1, okay? Then this means the left tail decays sub-exponentially. You get this limit. But also notice that as a function of alpha, this is a continuous function, okay? This is a continuous function. You get a different limit, get the different limit according to the value of alpha. And this is the first case in virtual case. Then we consider second one. So we still use the notation that we still assume that the number of springs is at least 2, and also need the notation need to be here. That means the minimum of the possible offsprings, okay? Then we consider another asymptotics of the left tail of x, that is the left tail of the x decays double exponentially, so e to the minus e to the z alpha for alpha positive. And then as for x less than x star, you can see the lower division probability decays also exponentially. Okay, you take 2 logarithm, then you get the rate function 1 over n to the power alpha over alpha plus 1. Then you have the limit on this right-hand side. This means that if you assume that the left tail decays exponentially, then the probability, the lower division probability also decays double exponentially. Okay, right? So this is the second case in the virtual case. Then the third case we want to say is that if the x is bounded below, we still need to assume that we are in the virtual setting, and we also need the notation need to be here. So if the essential infimum of x is just minus L, so it means it's bounded below, then the lower division probability still decays double exponentially. So it means that you take 2 logarithm of this probability, then the rate function is 1 over n, you get this limit here on the right-hand side. So log b appears in the limit, L also appears in the limit. And we also want to mention that here we assume x is larger than minus L because it's possible that the maximum is harder for the maximum could be lower than minus L times n, right? Because the essential infimum of x is just minus L. However, if the probability that x is minus L is positive, then this result also hold for the little x is just minus L here. So these are 3 cases that we considered in the virtual case. To summarize, I list all those 3 results in this next start. So first is that if the left tail of the step size decay at this rate, that is an exponential rate, then the lower probability also decays exponentially with the rate function over n alpha. And if the left tail of the step size decay double exponentially, and then the lower division probability also decays double exponentially, right? With this rate function. And again, if the x is bounded below, then this lower division probability also decays double exponentially with the rate function 1 over n here. And you can check that here in the second case that the left tail of the x decays double exponentially with e to the alpha. So you can imagine, okay, informally you can imagine, okay, if we let alpha go to infinity, so if it means the tail is very decays very fast. So in this way, it should be behaves like that the tail, the x is bounded below, right? So you can see that if alpha go to infinity, you get 1 over n here, okay? Get 1 over n here. You see in all the limit on the right hand side, you can see the little b here. That is the minimum number of the possible offsprings. You can also see the alpha here, okay, index alpha here, and also see the L here. I can explain why the little b appears in this in the limit. That is, we consider the basic ideas of this proof. So for the lower bound, you just suppress the branchings and the motions. How to suppress the branchings? Since we are in the shorter case, okay, so this means that there are at least b children, right? Since the little, according to the definition of the little b, it means the minimum of the possible number of possible offsprings. So at least when individual dies out, it at least has b children. So if we want to get a lower bound, you just suppress the branching that you let as before some time Tn, when each particle die out, it can only have b children, right? So you get a b regular tree, and then you also need to force at time Tn that all the individuals should be stay below to some places. Okay, that means all the individual at time Tn should be stay in some very low place. And after that works, so there are b to the Tn particles at time Tn. Then after that word, each particles will forms an independent branch random walk, but all those branch random walks will involve a Euro branch random walk. However, since all those particles are stayed in some very low place, so it's hard for them to get a very high place. Then you can get that the maximum for the whole system at time n is less than a given level. So this is the idea for the lower bound. That's why you can see the little b appears in the limit, okay? And also that's why we need to let all the individuals to be stay in a very low place. So that's why the left tail of the asymptotics plays a very crucial role for our result. Or this is just a lower bound. And for the up bound, the idea is somewhat similar, as you just try to see that the lower bound is optimal, okay? So you try to cut and regraph the marked trees. So why? Because that's why we need to assume that the random motion and the random branching are independent with each other. In this case, we can find a b regular tree up to some Tn. That is, you have a very bigger tree, right? But inside those bigger tree, you can find a subtree. Then this subtree is a b regular tree, and all the individuals at time Tn still stay in some lower place. And this b regular tree is coincides with the tree constructed for the lower bound. Then you can prove that the lower bound and bound matches. Okay, this is just idea to the proof. And also in Yun Hu's result and in our results, we also consider the moderate deviation. That is in the result presented here, we only considered the to minus the first order. Okay, to reduce the first order, but you can consider to reduce the maximum in any order. And we also can study the small ball probability for the limit of derivative martingale. So this definition of the infinity was also given in Bastian's talk, but in his talk, he considered the p of the infinity is larger than some x, but here we consider the probability that the infinity is less than some epsilon. Then we consider the rate of this decay rate of this probability as epsilon go to 0. Okay, then we can find that the basic idea to study this small ball probability is same to the to study the lower deviation probability. So I omit the details here, and the result in fact is parallel to the lower deviation probability for the centered maximum. Okay, so at the end I would like to summarize. The first is that this is the red curve is just a Euro decay functions for the maximum. And if we consider the up deviation case, you need to let the maximum be higher than this curve, okay, this blue curve. And if we want to consider the lower deviation, and you need to let the maximum be lower than these green curves, okay? So that's all. Thank you very much, okay, and good night.
Thank you very much for this very nice talk. So I propose that we just all unmute ourselves for a round of applause.
Thank you very much.
So are there any questions?
So I have a question about, you have these three cases, right? But
Yeah.
my impression is that your method of proof actually more or less goes through for other tails or for any tails, more or less.
Right. The idea could be applied to any tails. Yeah.
Right, but you have to do it each time again somehow.
You don't need to do that. I think the basic idea is the same. You just assume that, okay, you can replace the power here by some function fz, okay? Then maybe you may assume you may have some basic assumptions for this fz, then get similar result, I think.
Yeah, I see.
Mm-hmm.
Sorry, the upper deviation, which mentioned on last slide, what is the asymptotic of it? The x plus cn.
Sorry. So because here we consider we can enlarge the first order of Mn. So I replace the x by c in the picture. Okay.
So c is not important. Okay, thank you.
Yeah. It's just any constant could be larger than x star.
Thank you.
There is a question in the chat about whether it's possible to relax an in being of order n.
In, which where's
Oh,
in?
N, sorry.
Basically, if I
Oh,
just
sorry.
may interrupt, so your assumption at the end of the small deviation was that Ln was of the order O of n.
Yes.
Would this be possible to be different? Would this be possible to relax for any other different convergence order?
I think Ln is just how to say include all the possible cases, and it could be larger. I mean, it could be even larger. For example, it could be n to the power or n square or something like that.